In this video lesson, we're going to work our way through the free fall and Newton's second law worksheet. So right now I have the medium spice one open. And what we're doing here is the following picture is a skydiver. Assuming no air resistance, calculate the following velocities and distances falling. And use these equations. So you'll notice these equations do go back to our previous unit when we learned about motion. That's okay. I mean, we still have the information, so we'll use those equations as well, and it's always good to review because a lot of these physics units do tie together. So, anyway, taking a look at this. The very instant that he jumps out of the plane, he is going to have a final velocity of 0 meters per second, a distance of 0 meters, and direction that of the acceleration is down because gravity is going to be pulling him down. And that's why time is 0 seconds. Now, after 1 second of falling, we want to know, well, how fast is he going? So we have our equation, Vf is equal to Vi plus gt. Well, his initial velocity in every case is 0, because the very moment he jumps out of a plane, he's not going up, he's not going down. That very instant time, he has an initial velocity of 0. So now we go to solve for this, and we say Vf is equal to Vi plus gt. Well, in this case, our initial velocity was 0 meters per second plus gravity, which is 9.8 meters per second squared, times our value of time, which is right here, of 1 second. So therefore, we find that their final velocity is going to be 9.8 meters per second squared. Distance, on the other hand, we have to use a different equation. And so I'm going to get rid of this other info here, except for it's not letting me. There you go. Sorry, need to clear up some space. So now we go through, and to solve for distance, we're going to use this other equation. Distance equals 1/2 gt squared. So we know distance is equal to 1/2 gravity times time squared. Well, we know gravity is 9.8, so we're going to have 1/2 of 9.8 meters per second squared times our time of 1 second squared. So we take our 1 squared first because we want to follow that order of PEMDAS, so parentheses, exponents, multiplication, division, addition, subtraction. So we have to take our squared first, so we have 1 squared is 1 times 9.8 times 1/2, or divide by 2, same thing, and you will get an answer of 4.9 meters. And the direction of their acceleration is still going to be down. Using those same equations for the next couple problems, we would have final velocity is equal to our initial velocity of 0 meters per second still, plus gravity times time, which in this case, gravity again is still 9.8 because we're still on Earth, times our time of 2 seconds. And we find that our final velocity is going to be 19.6 meters per second squared. Distance, we're using that same equation, 1/2 our gravity of 9.8 times our time squared, and our time squared is going to be 2 squared in this case, so we have 2 squared is 4 times 9.8 divided by 2, and that's going to give us an answer of 19.6 meters covered as well. And then they are, of course, still accelerating downward. Alright, looking at the third problem here, if we go through and do it again, Vf is what we're solving for. Initial velocity is still 0, plus acceleration due to gravity is 9.8. And then we need to multiply that by the 3 seconds that it's been falling for in this case. And we will see that the velocity is 29.4 meters per second. Now if we switch over to solving the distance, we're using that same equation. That distance is equal to 1/2 gravity squared. So that is 1/2 times 9.8 times our time squared, which is 3 squared. So in this case we take 9 times our 9.8 times 1/2, and we get an answer of 44.1 meters. And again, because the object is falling, the direction of its acceleration is still down. Now if we take a look at the next questions here, find the acceleration of the boxes using Newton's second law of motion. Please remember Newton's second law of motion talks when net force is anything except for 0. So that is when the net force is not equal to 0. First thing you always want to do in order to solve one of these problems is you want to find, well, what is the net force acting on this object? So again, thinking about like a tug of war, if you have 9 newtons pulling this direction, 2 newtons pulling the other, the resultant net force is going to be 7 newtons. So therefore, to solve for the acceleration, we need to use our acceleration is equal to net force over mass equation. And therefore we take 7 newtons divided by our mass here of 10 kilograms. And we find that our acceleration of this box is going to be 0.7 meters per second squared. And the object is going to go, again, according to Newton's second law, an object accelerates in the direction of a net force. So the object is going to be accelerating to the right because the net force was acting to the right. Looking at the second problem now, it gets to be a little bit trickier to solve. Since these forces are not pulling opposite of each other, we actually need to use the Pythagorean theorem to solve for them, and we need to think of them as a triangle. And in this case, we're going to say that we're going to use our equation a squared plus b squared is equal to c squared. So therefore, the square root of a squared plus b squared is equal to c. So we plug in our values, we get the square root of 2 squared plus 9 squared, which again, sorry, I'm running out of space, is the square root of 4 plus 81, which is equal to the square root of 85, which is going to be equal to 9.21. But again, that is still not our acceleration, that is just our net force, or the overall change in our force. So now we need to take that answer of 9.21 newtons divided by the mass of the object, which again is this 10 kilograms. And you find that the acceleration of the object is 0.92 meters per second squared. Sorry, it's really bad, 9. And the object is now going to be accelerating up and to the right. Alright, now I'm going to go ahead and get rid of some of the work from the previous problem, just to clear up some room here. So what this question wants us to do is to label different forces acting on this picture. So this guy's pulling this direction, so he's going to have an applied force. Friction is going to oppose that force, so you have friction acting backward. You have a force of weight acting downward, and then there's going to be a normal force acting upward. So this first question asks, if the pulling force is 150 newtons and the box doesn't move, what's the magnitude of friction? Well, you can't have an exact number, but you just know that it is going to have to be greater than 150 newtons. Because if he's exerting 150 newtons of force and the box still doesn't move, Well, it must have force of friction greater than 150 newtons. Looking at question number 2, if the force of sliding friction is 250 newtons, what force is necessary to keep the crate sliding at a constant velocity? This actually ties in with Newton's first law of motion, where it says an object in motion stays in motion, object at rest stays at rest. So if the object keeps sliding with a constant velocity, the force to keep it going at constant velocity is also 250 newtons. If you had a greater force, the object would be accelerating, not at constant velocity. If the object had a smaller force, the object would be slowing down, or therefore accelerating negatively. Alright, let's go to the second page of this worksheet. Okay, looking at the second page of this worksheet. The following is a picture of tandem skydivers where gravity and air resistance are both forces acting on them. So both of them are tying into this one. In the previous unit where we learned about motion, we often ignored air resistance. Now we are going to factor it in. The first skydiver has a mass of 98 kilograms, the second one a mass of 102. Since they are tandem, that means they're strapped together. So we're just going to go ahead and simplify this and say that their mass is equal to 200 kilograms. Because that's their combined mass. Calculate the net force and acceleration for each picture. So, also before we get started on this, let's just rearrange the equation to solve for acceleration, which we've already done on the previous page. And we know that acceleration is equal to net force divided by mass. Except for my handwriting right now is terrible. Alright, force of weight. We also learned in our Newton's second law notes that force of weight is equal to mass times gravity. So in this case, the force of weight of these guys is just going to be 200 kilograms times gravity, which is 9.8 meters per second squared. So they would have a force of weight then 1,960 newtons. And since this picture is when they initially jump out of the plane, they don't have any air resistance yet, hence why there's no up arrow here. They just jumped out of the plane. We're just saying, okay, their force of weight is 1960 newtons. So therefore, the net force in this case, that is the overall change of force, doesn't need to be solved for. We only have one force acting on these guys, and that is their force of weight. Therefore, the overall change in forces is 1,960 newtons. To solve for acceleration, we're going to take that net force of 1960 divided by the mass of 200 kilograms, and you get an acceleration of 9.8 meters per second squared. And hopefully that kind of makes sense because it's the only force acting on them. If there's no force of air resistance, gravity should be able to pull them down at 9.8 meters per second squared. And so again, the direction of their acceleration is downward because Newton's second law, an object will accelerate in the direction of net force. Their net force is downward, therefore their acceleration is downward. These next couple examples are where things get to be a little bit trickier. So their force of weight is still going to be 1960 newtons. Their force of weight isn't changing because their weight is the same the whole time. No matter where in the free fall, their force of weight is the same. What is going to change, however, is going to be the net force. Because now you look at this problem and you see, oh, we're talking air resistance. They have now been falling for a little bit. There are more air molecules hitting them as they fall. Therefore, their force of air resistance is now 500 newtons. And their force of weight is 1960 newtons. Therefore, the net force is going to be 1960 minus 500, and you'll get an answer of 14. It's really ugly for 1460 newtons. Because again, just think of it like a tug of war. They're pulling in opposite directions, so they kind of cancel each other out, and you get a net force of 1460. To solve for the acceleration, you're going to take that net force of 1460 newtons divided by the mass of 200 kilograms, and this will give you an answer of 7.3 meters per second squared. And that should kind of make sense. It's kind of like when you drop a sheet of paper and you can see that the air resistance is slowing it down. The sheet of paper isn't falling at the full 9.8 meters per second squared from gravity because there's a bunch of air resistance. Same thing here. These guys now have air resistance acting on them, so they're not accelerating as quickly as they could. And so your acceleration goes down a little bit from what it was in the previous problem. But their acceleration is still downward because the net force, or the force acting downward, is greater than the force acting upward. So their acceleration is still going to be down. Taking a look at part C, you can now see that their force of air resistance is 1960, and we also know that their force of weight is 1960 at every point. So now they've deployed their parachute, their force of air resistance, and since these forces are both 1960, well, that's a pretty even tug of war. Therefore, their net force is 0 newtons. They just deployed their parachute. It turns out air resistance is equal to force of weight, and therefore they have 0 newton net force. So now to solve for their acceleration, you take 0 newtons. Oops, sorry, the iPad switched there. So 0 newtons divided by a mass of 200 kilograms, and we know that anything divided by 0 is 0. And now is where students start getting a little confused. Well, how do they possibly have an acceleration of 0 meters per second? Does that mean that they just stop in the air? No. Please remember the difference between acceleration and velocity. Velocity, the objects are moving. They have a speed. But if acceleration is 0, it just means that they have a constant velocity. So they're just going a continuous speed downward. They're not speeding up, they're not slowing down, they're just going at the same speed that they were right before they open their parachute. And now the direction of acceleration, well, really they don't have one because they're not accelerating. And taking a look at the last one. So here we have force of air resistance. The parachute is now fully deployed. Force of air resistance is 2100 newtons, and their force of weight is still 1960 newtons. So in this case, their net force is going to be this 2100 minus 1960, and so the overall resultant force is 140 newtons. So to solve for acceleration, we're going to take that 140 newtons divided by an acceleration of 9.8 meters. I'm sorry. I don't know why I suddenly started thinking that. Divided by a mass of 200 kilograms. And you will get an answer of 0.7 meters per second squared. And what's weird with that is, let's think about the direction of acceleration. So again, Newton's second law says that object will accelerate in the direction of a net force. So looking at these two forces over here, since this force is greater, technically this is the direction of the net force is upwards. So these objects, or these people, are accelerating upward. And again, this is where things get to be confusing for students. Just picture though, when somebody's skydiving, are they ever going upward? No, they're not. They're always falling downward. The earth is always pulling them back down. So what does this acceleration of 0.7 meters per second squared upward mean? It means that their speed is changing in an upward direction. So if they had a velocity downward, which they do because they've been falling and they've been gaining speed while they fall, but they have an acceleration upward, it just means that the object is slowing down, similar to when a car is traveling. If a car is traveling this direction, they're slowing down, their acceleration is this way. It doesn't mean that the car is moving to the left. It would just mean that its acceleration or its change in velocity is to the left, even though the car itself is still moving right. Same thing here. The parachuters are still moving downward, but they're slowing down in this case. So question 1, at which position A, B, C, or D are the skydivers going the slowest? Be careful with this one. We are now talking about speed. We are not talking about acceleration. So we can't go back and look at these problems up here and just simply look at, oh, they had an acceleration of 9.8 and 7.3. That's not when they're going fastest. The very instant they jump out of the plane is actually when they're going the slowest, because they had just jumped out of the plane. Acceleration hadn't picked up their speed yet. As they're falling, they're going faster and faster until this moment right when they open their parachute is actually when they were going the fastest, because as an object falls, it keeps gaining speed. So at which position are the skydivers going the slowest? They're actually going the slowest at position A. Question number 2, at which position are skydivers going the fastest? Well, they're going the fastest at position C, because that is right before they open their parachute. And then at which position A, B, C, or D are the skydivers falling at constant velocity? Again, constant velocity means that there's no acceleration. They're not speeding up, they're not slowing down. And that was at position C as well. They had no acceleration, therefore they're going to constant velocity. So therefore C is your correct answer.